idea of chemical reactions, we use chemical equations to represent the chemical reaction. So we go reactants, reaction arrow, products. And we've talked about balancing chemical equations. So as it turns out, if you have 2 in front of the C4H10, by the way, is a hydrocarbon, this is the thing we're burning. If you combine it with 13 O2s, it will form 8 CO2s and 10 H2Os. So we're going to actually do some problems like this, where we could draw a brick wall and come up with the same number of carbon, hydrogens, and oxygens on either side of the brick wall. We could prove ourselves. You come up with 8 carbons, 20 hydrogens, and 26 oxygens. Okay, looks like the word is pollutants here in the last paragraph. So this just says that we're going to kind of look at combustion or burning things in a simplistic way, even though it's a little more complicated than that. We do that all the time in introductory courses like this. So let's see what we can do. Now, I'm going to go around the room and ask you specific questions, and we're all going to balance these, if that's okay with you. Even if it's not, that's what we're going to do. So we'll start with you, Autumn, and then we'll go over to you, Natalie. So first off, this is my question to you. Sucrose has carbon, hydrogen, and oxygen in it. My question to you, and you can get it wrong and there'll be no penalty, but is this an example of a hydrocarbon? No, because it has something else in it. This is not a hydrocarbon. Because it has hydrogen, carbon, and oxygen. Perfect. Okay, Natalie. Now you can look at the previous slide if you want to, but when we burn something, I'm going to go ahead and put, this is one of my reactants, C6H12O6. What do we combine it with? What's the other reactant? You can look at the previous slide to see what the other reactant was. The thing we burned on the previous slide. So we had the hydrocarbon plus what?
Are you talking about this equation?
On the previous slide. So we had this, and plus what did we react it with?
Oxygen.
Yep, that was all I was after. Yep. So we reacted with oxygen. I'll put O2 there because remember that oxygen's always got a buddy. So now back to you, Billy. What does it form? What am I going to put on the product side? And it takes the same pattern as the previous equation. Carbon dioxide and water. Yep. Exactly. Okay. I'm going to probably, what's that?
Oxygen always got a buddy?
Yep, oxygen, if oxygen's just floating around like 20% oxygen in the stream, it's always going to be diatomic. It's going to be an O2, what we call molecule. Yep, it'll never be by itself. And hydrogen's like that's the, I don't know, the Hoffer nickel. So hydrogen does a buddy, oxygen, bromine, fluorine, nitrogen, bromine, if I said bromine. Okay, so back to you guys in the rear. So I'm going to have to actually, I don't know, I'm going to run out of room, so I'm going to have to erase this here in a minute. But I'm going to go carbons, hydrogens, oxygens, carbons, hydrogens, oxygens. Okay, and so help me out, Taylor. How many carbons do I have over here if I go with a coefficient of 1? I have 6. Okay, Glenna, how many hydrogens? 12? Autumn, how many oxygens? Make sure you get everything over here. So this is a brick wall.
8.
I have 8. 6 plus 2. Okay, Natalie, on the product side, how many carbons do I have? 1. Billy, hydrogens? 2. Taylor, 3 oxygens. Perfect. So what I told you before when I balance these is I usually put a big a line to the left of each species saying that I can go ahead and put a number in there. So we're up to you, Glenna. Let's see. To me, I'm a little heavy over here on the reactant side, so I'm going to go on the product side. So Glenna, help me out. How can I get my hydrogens to balance?
6.
Yep, put a 6 in front of the H2O. So Autumn, if I put a 6 in front of the H2O, help me out. Can you update my, well, hydrogens, I'll go ahead and change them to 12. But Autumn, then how many oxygens do I have? I have 8. I'm liking it. So I'm updating my oxygens to 8. Okay, Natalie. Let's see. The thing that's not, wow, our oxygens just kind of fell into place. Hydrogens. Now carbons aren't right yet. So how can I get the right number of carbons on the product side? If I need 6, how can I get 6 carbons over here? If I put a 6 here, if I put a 6 there, that means I have 6 CO2 units. And that does mean that I have 6 carbons. So I'm going to update my carbons to 6. Now, Billy, help me update my oxygen. Since I put a 6 there, now I have different numbers of oxygens. So when carbons are 6, how many are my oxygens? 18? Sometimes I have to get a calculator out for this. Let's see, 12, I agree, 18. So again, it's kind of a back and forth sort of process. So it looks like we have 8 on both sides. We have 6 carbons on both sides, but our hydrogen stayed 12. Thank you. Sorry, hydrogens didn't change. This is what changed, right, Billy? That 8 changes now to 18. Is that better? Yeah, that's much better. Okay, so our carbons and hydrogens are okay. So we're back to you, Taylor. So how do I fix my oxygens? I need to have 18 oxygens over here and I only have 8. Put a 9 in, wait, yep. Now be careful because like we have some here. So we have 6 brought here. So what would I put here to make a total of 18? So I don't need, what's that? 6? Yeah, I'm liking 6. If I put a 6 here, that'll give me 6 times 2 or 12, plus the 6 brought by this. 12 plus 6 is 18. If I put a 6 in front of the O2. We good with that? Any questions? So that's the balancing that we've talked about. I can confirm that by my looking one more time at my carbons, hydrogens, and oxygens, but I am feeling good about that. Let's do one more. I'm gonna have to, is it okay if I erase this? Okay. So otherwise I won't have room. All right, so let's do this one. So I think we're up to you, Autumn. We're gonna do kind of a similar thing. So CH4, if we're talking about combustion, what's it gonna react with? Did I skip you, Glenna?
Yeah.
Okay, it's gonna combine with oxygen. So Glenna, what's gonna be produced? 2 things.
Carbon, whatever. Carbon and the hydrogen, or the carbon dioxide, or carbon.
Yep, carbon dioxide. And then what else? Same pattern as what we did before. Water. That's it. When you're burning fuel in your vehicle, you're burning hydrocarbon basically. And have you ever seen it, like, especially in cold weather, come out your tailpipe, some of this liquid going out your tailpipe? That's basically just condensed water. Okay, so we're over to you, Natalie. We'll go ahead and put squiggly marks here to the left of everything. Here's my brick wall. Have carbons, hydrogens, and oxygens. Carbons, hydrogens, and oxygens. So what do we have? How many carbons do we have on the reactant side? 1. Billy, how many hydrogens? On the reactant side. Did you say 4? Yep. Taylor, how many oxygens? 2. Glenna, over on the product side, how many carbons? 1. Autumn, how many hydrogens? 2. Natalie, how many, 2 hydrogens, good. Natalie, how many oxygens? 3, perfect. So back to you, Billy. Let's see. If I was balancing this, which we're doing it together, I might would just help me out with the hydrogens. Let's get the hydrogens right. So what am I going to do? I put a 2 here in front of my H2O. Yep. And let's update. So Taylor, how would I update? So I'm going to go ahead and update my hydrogens to 4. So what's an update for my oxygens then, Taylor? I think you were right the first time. There's 2 there. There's 2 here. And then there's 2 here. So 2 plus 2 is, yeah, it goes just to 4. Yeah, because all we did was kick in 1 more H2O. So my 3 is going to be a 4 now. Okay, so Glenna.
Can you go ahead on the oxygen with the 2?
Yeah, that was going to be my question. How are you going to fix the oxygens? And you're saying if we put a 2 here, that goes ahead and gives us 4 here, and then we're set. Yep, exactly. 2 here, and then update for the oxygens. I got 4. And we are A-OK. Okay, so combustion. I'll read that last one. So one of the reasons, energy. I mean, why do we burn fossil fuels for energy? Whether it's in our, we want thermal energy, we're burning it in our gas burners, or whether we're burning it in our car, so it turns to mechanical energy, basically. Okay, so we need to talk about energy. So energy is the ability to do work. Sometimes I feel like if you have, it's like, oh, man, I have no energy. Well, you have no ability to do any work. And that's how I feel sometimes. We talk about 2 types of energy. There is stored energy called potential energy. This says energy due to position or composition. I would say potential energy is stored energy. You know, an example of potential energy is like when you need to mow the lawn and you go to the gas station and you fill up your gas tank. As that liquid, that fuel is sitting in your tank, that's potential energy, not doing anything. It's stored energy. The other one is kinetic energy. And this says movement, but you'll hear me say, I think of kinetic energy as energy associated with motion, movement or motion. Okay? If I'm moving around, actually our bodies are so complicated. We are, moving is work. And in order to do work, we need to use energy. And so what our bodies do is we basically burn fuel in our bodies to accomplish work. So there's all sorts of different types of work. A simple work is this. Work is basically you are applying a force over a particular distance. Now there's also, sounds like a physics thing basically. And for instance, if I relocate this, okay, I could take my finger and this would be horizontal movement, okay? I have to apply a force, okay? And the force I apply times the distance I relocate it is the work that's done. Kind of silly, but it's true. There's all sorts of different types of work. So one of the things I want to talk about is this idea of heat or thermal energy versus temperature. Heat versus temperature. And you might use them as interchangeable, but they are not. Temperature is a lot simpler than heat. Heat and thermal energy are synonyms. Now, one of the things that among things heat and thermal energy will do is you'll know the direction that thermal energy will go. Thermal energy will always go from something that's hotter to something that's cooler. I've got this little video here to kind of show you if this works.
Molecules of a hot substance move more rapidly than those of the same substance with a lower temperature. If the two samples come in contact, a transfer of molecular momentum occurs from the rapidly moving molecules to the slower ones. In this way, thermal energy transfers from the hotter sample to the cooler one. When the two samples have similar rates of molecular motion, they have the same temperature.
So a few things here, and a lot of times students already intuitively know this. Well, maybe you don't know this, but all matters, all atoms that make up matter have a certain amount of motion. Okay, whether that's just vibrational motion, or whether that's translational motion. Okay, all matter has motion. And a minute ago, I told you what motion was. So what sort of motion, what sort of energy motion is? I said it's kinetic energy. So as it turns out, all matter has a certain amount of kinetic energy. Now, the video we saw started out with like red and blue. Okay, which one was going faster? The hot ones or coolers? The hot ones. Hot ones were going faster. Yep. And so that's kind of the deal of it. Is it's that simple. When you heat up something, if we were to look at the atomic scale or whatever, they're moving faster. Okay. And I like this little video because it showed kind of the stuff that was moving faster bumps into the stuff that's moving slower. It loses some energy, and these guys pick up energy. So, I don't know, what do you think? One of the things like on a cold winter day is we open up the door and we're like, oh man, you feel the cold air rushing in? Well, technically, your hot air is rushing out, okay? Now, this video says that you're going to ultimately reach some sort of equilibrium. That's not going to happen, okay, because you have the great outdoors and you have your house, okay? So you have different volumes of temperatures. But thermal.
If you left your door open long enough, it would.
If you left your door open long enough, it would.
Oh, that confuses me.
What's that? Because the cold air.
Yeah, but.
You know, the thing about the hot air. The hot air rushes out. I know, you're like, how do you know that? Well, it just makes sense, but we do feel cold air coming in. And to me, I think what happens is the hot air rushes out and it creates a vacuum, and then the cold air comes in. So I'm not saying the cold air doesn't come in, because it does. But the hot air is more aggressive. So
that kind of makes sense, but like creates like a circle. Like
yeah, like a circulation cell. Yeah, I think so. Yep. So temperature is simpler than heat, okay? Thermal energy and heat are the same thing. Temperature is just like, I got a temperature probe. I'm gonna stick it in this thing, see how fast those little molecules are moving. What sort of motion they have, that's temperature. So thermal energy is much more complicated than heat. So we say heat is a consequence. How much thermal energy or heat something has is a consequence of kind of how fast they're moving, the temperature. With regard to heat, the units that we use, of course, there's always metric and English. Okay. When we did our lab last Tuesday, oh, by the way, this Tuesday we're gonna hopefully make some biodiesel fuel. But the units of energy that we used were calories. And actually, as it turns out, that is an English unit. The metric unit is the joule. So units of energy. I actually brought a prop along to show you this. Over here is a 1 kilogram weight. I've never heard this definition before. I've heard different definitions of joule. So we take this 1 kilogram weight and we raise it 10 centimeters. So I'll pass this around. So you have to take the base of it and raise it, let's see, so these are in centimeters. Wow, that is pretty far, 10 centimeters. So you take this and you raise it 10 centimeters. And you have expended 1 joule of energy. I dare you. Well, that's a good idea. 1 joule? Does it feel like 1 joule? Throw my shoulder out. It's kind of hefty. What's that? Is it Ta-da! Ta-da!
That is kind of, yeah, that was kind of cool.
Yeah. 1 joule, that's kind of cool, right? So joule is English, calorie is metric. We're going to talk about, if you flip over a candy bar, actually, they say the calorie content on a candy bar, and it's related to this calorie, sort of. This is actually what we call thermodynamic calorie, and that's a dietary calorie. But I like the definition of a calorie is if you were to get 1 gram of water, 1 gram, 18 grams is about the size of your volume of your finger. So it wouldn't be very much. 1 gram of water, it'd be about 1 milliliter of water. And you were to zap it with enough energy to increase the temperature 1 degree Celsius, that's 1 calorie. Okay, that's 1 calorie.
So if you heat your food up, there's less calories?
Well, if we heat our food up, we're pushing we're pushing energy in. One of the things I've heard actually is I've actually seen kind of the math on this. If you eat ice cubes, okay, what happens in your stomach is that you have to work to bring that ice cube up to your body temperature.
Yeah, that's so it's technically burning calories.
Right, right.
Is that how this is?
Celery.
Celery's a negative calorie food.
I think that's why they say when you're sick, you eat soup because it's hot.
I don't know.
If you're dying of dehydration, you can't eat snow because it takes more energy to heat up than you're getting.
That sounds kind of consistent with, yeah.
So if you're dying of
What? Not dying? Tell me. Yeah.
and there's snow, you should try to melt it in some way before you eat it because the energy that your body will use to turn that to water is offsets the hydration. So if you drink hot water, is that giving you energy?
Sort of. Hot water.
It warms you up.
Yeah. Yeah, it gives you, it adds thermal energy to your bodies.
I've never thought about that.
Interesting.
They say that, but if you're dying,
You're gonna eat
you're gonna eat the snow.
It'll melt in your mouth a little.
Yeah.
Well, thanks for that pleasant thought of dying or not dying. Anytime. So the way this works between the English and the metric system is this. So 1 calorie is equal to 4.184 joules. Now, this is what we call, and I'll even put the word up here, an exact relationship. And not all equivalencies are exact, but this is totally exact, kind of by definition. So it's kind of a fun sort of thing. Now, hopefully this is case sensitive. So this is a calorie with a lowercase c. This is what we call a chemistry calorie or a science calorie, a thermodynamic calorie. When you flip over your candy bar is actually talking about, your candy bar hopefully doesn't talk, but the information on your candy bar is an uppercase C, C-A-L, calorie, big C. And this is what we call a dietary calorie. And the science calories, okay, it takes 1,000 science or thermodynamic calories, lowercase c's, to make one big C. Hey, that makes sense, because like lowercase is less, and then, okay, so it takes 1,000 of those to make one dietary calorie. So the candy bar calories are over here, okay? And they are related to, so I have a question coming up, and we're going to use that to our advantage. A slice of pizza contains 217, contains 217, that seems kind of low, doesn't it, calories? Oh no. It's a small slice. Must be, okay, small slice, yeah. Okay, these are, the big C means thermodynamic calories. What did I say is the relationship between 1 calorie is equal to how many joules? 4.184. Yep, 4.184 joules. Perfect. So to work this is how I would do it. And let's see, let's go around the room. Who do we end up with last? We're making kind of a circle in here. Taylor. No one else. Okay, so Autumn. We'll start it this way. I'm going to go 217 kilocalories. So kilocalories. So help me out. Let's see.
Wouldn't you want to go ahead and take it times 1,000?
Yeah, that's what I was going to say. So we'll start with you. Go ahead and say. Glenna, no, honestly, that's what I would do. So how would we get that to just calories from kilocalories? You said 1,000?
Yeah, well, 1 kilocalorie equals 1,000 calories.
Yeah, 1 kilocalories equal 1,000 calories.
So you times it out.
Yep, times it out. And then if you're okay, what I learned is I'm just going to kind of keep going with that thought. I'm going to put another term here. But when you multiply it out, you get calories. So, so someone help me out. Just shout it out. How am I going to get from those calories to joules then?
Take that times the 4.18.
Yep. Take that times the 4.184 joules. Okay, per 1 calorie. Yep, it's all looking good. So then how am I going to get it to kilojoules? So now my calories cancel and I have joules. How am I going to get to kilojoules? I'll go ahead and put joules on the bottom and kilojoules on the top. What's the relationship between joules and kilojoules? What's that? So joules are on the bottom, kilojoules on the top. So my point is blank kilojoules is equal to blank joules.
Did we talk about those? 1,000 kilojoules.
1 kilojoules equal to 1,000 joules.
So then we'd have to take that number times 1,000 too.
When you divide the whole thing by that?
Yeah, I'm liking divide by because the way this works is if I take the 1,000 joules on the bottom, 1 kilojoule on top. So then my joules cancel. and I have the units of kilojoules. It always, if I work it this way, I'll divide or multiply the right way. So can somebody put that in their calculator and give me 3 sig figs?
907. 907. Is it?
907. Yeah, kilojoules. What do you think, Billy?
Sounds good.
And you could go ahead and break it out and like do individual problems, and you should get the same number.
I don't understand why you do times by 1,000, because they give it to you in calories. 217.
Yeah, they give it to you 217, but this big C means that's the dietary, like that's the candy bar calories.
Oh, okay.
Yep. And so actually, there's a factor of 1,000. So if you go back to the previous slide, it said that 1 kilocalorie is equal to, yeah, there it is. 1 kilocalorie is equal to 1 calorie. Okay.
Yeah.
What's that? What do you think, Billy?
We need to take it times 1,000 and divide it by the 4.1.
Did you get the same number? Because if you can work it a different way and get the same number, that's fine too. Because people think of it differently, different ways to work it. How's your chair, Autumn?
Great. And I can see.
There's one more chair over there.
Would it be 908?
Right.
Yeah, I guess it.
908. Okay.
Picky, picky.
Thank you. Okay, so follow-up question looks like this. So you eat the pizza, how many 1 kilogram books can you lift off a shelf, but it's not just 10 centimeters, it's 2 meters.
Depends on how strong you are.
Hey, you just eating pizza, you're way strong. So 2 meters, so down there, so this is 1 meter, so wow, dang, okay. So 1 slice of pizza gave us, what do we say, 908 kilojoules. Calculate the number of books. Yeah, let's skip this one. I do too. I find it quite irritating. Okay, on to something different. It is different, but not really. So I'm going to kind of reveal these going from the lower energy up. And these are in units of joules. So 10 to the negative 21st joules. That's how much motion or kinetic energy that an oxygen molecule has. Oops. Well, my builds don't work. That stinks. You are evil. All right. It only does what you tell it to do. We got this. Sort of. So you've got the whole slide. I just put it. All right. So this is just supposed to kind of put in perspective kind of the energy in joules. So let's jump up to This one, the amount of energy required for a computer chip to perform a simple mathematical operation. You know, somewhere between 10 to the negative 12 or 10 to the negative 9 joules. Energy required to lift an apple. Anything raised to the 0th power actually is 1, so you're looking at 1 joule. Those batteries that we use, you're looking at 10 to the 3rd joules, so that's like, what, 1,000 joules? Light bulbs, 5 hours of use, 10 to the 6th joules. A barrel of oil, 10 to the 9th joules. Energy of the first atomic bomb, 10 to the 12th. Energy released by earthquake, magnitude 8.3, between 10 to the 15th, 10 to the 18th joules. There was one more at the top. I thought this last one was weird. You're like, are you serious? What a weird thing to think of. This last one says, you know, we said it took a certain amount of energy to heat, a gram of water. It takes 1 calorie of water to bump that temperature up 1 degree. Well, if you were going to add energy to heat the entire volume of the Earth by 1 degree Celsius, it would take 10 to the 24th joules. That's so strange. Maybe he's talking about global warming. I don't know. I just find that one strange. All right. This gizmo is called a calorimeter or a bomb calorimeter. And the way it works, the word looks like I kind of hid there is combustion. The way it works is you have an inner chamber where your combustion is going to occur, and it actually has water around it to help absorb the energy that's released during combustion. You have this little kind of red thing that kind of goes in to help you ignite it. Okay, so again, this is water. Okay, and this is where your reaction is going to occur. You have some sort of stirring, and then of course you have a thermometer to measure the temperature of the water as it goes up after it's heated from your combustion. That's it. That's totally it. So, oxygen inlet. That's important. Wonder how that oxygen inlet. So it would have to have like some sort of, because they're not showing it here. If this is water, then you'd have to have some sort of tube that lets oxygen come in. Okay. And it goes back to kind of finally what you guys did last Tuesday. One of the things you did with the different fuels, the 4 different fuels that you burned, is you came up with energy released per gram of substance that you combusted. So in this case, it's energy per molar gram. All right. So I want to talk about these 2 types of reactions, one that give off energy, called exothermic, and then one that takes in energy, called endothermic. So exothermic reactions are going to release energy as the chemical reaction occurs. All of our combustion reactions would be exothermic. So for instance, if we burn methane, CH4, it's going to release 50.1 kilojoules of energy for every gram of methane that you combust. If we were to convert from grams of methane to moles of methane, okay, same chemical reaction, you're looking at 802.3 kilojoules of energy per mole of methane that's burned. So this down here at the bottom kind of shows you how that conversion happens, or how we convert from kilojoules per mole to kilojoules per gram. So, for instance, if we know that it's 802.3 kilojoules per 1 mole, in order to get to grams, we're going to use the molar mass of methane. And remember what we do is we go to the periodic table, got mine handy here. We look up 1 carbon plus 4 hydrogens to get a molar mass. And then you will get 16.0 grams per mole. That's the molar mass. So we use the flipped version of the molar mass, so moles will cancel. Unit-wise then, we have units of kilojoules per gram. With 3 sig figs, then this is your answer, 50.1 kilojoules per gram of methane. So again, this guy right here, this is your molar mass. We get that from the periodic table. Okay, so exothermic. Combustion are exothermic reactions. Sometimes I like to kind of show it this way, where we have methane, and this won't be a balanced equation, but we've been saying how you could take CH4 plus O2 goes to form or reacts to form CO2 plus H2O, and then I'll actually put energy over here. And that is showing an exothermic reaction. On an energy diagram, it would look like this, where energy diagrams don't have anything along the x-axis. They basically have something along the y-axis. And as you go up, you're increasing energy. So in this case, the energy associated with our reactants, what we start with, is is greater than the energy that we end with. So it's like an energy, it starts here, that would be our reactants, and it ends over here, that's our products. And then what's released is energy. Okay, not all fuels are equal. Looks like I have the word heat energy. And you guys definitely saw this in your lab last week, where depending upon which fuel you grab. In general, fuels that have the highest, fuels with the highest heats of combustion will be your hydrocarbons. So I've got kind of 4 or 5 different things being burned. This one's methane being burned. Okay, you see the energy decrease from reactants to products is 50.1 kilojoules per gram. Octane, C8H18 plus 25 over 2 O2s, that's to balance it. Notice it's less. Plain old carbon and oxygen, burning carbon, that's coal. To release energy, that's even less. When we introduce an oxygen, so it's not a hydrocarbon anymore, this is actually, this OH makes it an alcohol. So this is ethanol. Burning it is even less. Burning glucose or wood, C6H12O6, it's even less. What is glucose? Glucose? Well, glucose is sugar. So, but then, why does it say glucose? Yeah. Well, I think they're using kind of a similar repeating unit that's in wood is also in glucose. So, I think. So in general, as the ratio of hydrogen to carbon decreases, the heat of combustion also decreases. And as the amount of oxygen in the fuel increases, you'll also have a decrease in the heat of combustion. That's a good place to stop. So all this talk about fuels, we'll see if you guys can make some fuel from vegetable oil tomorrow. Oh, that's right. So I was going to give you guys a, check your emails and I'll try to send you the format for tomorrow's lab.
It seems like if there was more oxygen, it would burn hotter.
But if you figure that oxygen kind of takes up the spot, in a sense, and oxygen doesn't combine with oxygen to form. On the product side, the things are going to be your H2O, which takes from the hydrogens from the hydrocarbons, and your CO2, which takes from the carbons from the hydrocarbons. So your oxygens are kind of along for the ride, like in the alcohols, so they don't add to the energy.
I think of like a wood stove when you open up the.
Oh, well, that's different. In that case, you're getting more oxygen. You're getting it more.
And it burns fast.
Yeah. This is talking about oxygen in the compound. So this would be talking about this oxygen here. But yeah, you're right. If you increase your O2, you're just gonna burn faster.
It's all about the blend.
Yeah. It's all about the blend.
I used to well.
Okay.
All different kinds of tanks.
Yeah.
Non-flammable. So
Okay. Non-flammable what?
I TIG welded.
Yeah.
The gas we use to TIG weld is non-flammable.
Okay.
You fuse it with electricity, with current.
Interesting.
Yeah, it's different. TIG welding is a little different than the other way.
Mm-hmm. Cool.
Take it when you got the stick and you gotta feed it.
Yeah, you gotta feed it. You heat up the boil a little spot with a tiny torch, and you feed your stick into it. TIG welding is incredibly boring.
Yeah, which one's the easy one, right? Or
TIG welding.
take it the easy one?
It's incredibly
Maybe it's when you gotta like do it at the same time. It's not.
That's what it feeds.
Yeah.
It's constant. It's sloppy. I'm done. We're trying it all anyway.
Sounds interesting.